Welcome everyone to AML Conversations Meetup. A lot of people coming here, right? And I want to introduce ourselves. Myself, it's Vladimir Ermin. I'm a data scientist and machine learning engineer. And my co-host for tonight, we are the co-founders of AML Conversations. And this meetup we've been running for almost a year already, and I want to give you a very quick story of what is this meetup about. As you can guess, it's around data science and machine learning, and it started as a just informal meeting of friends over the bar, and we slowly grow it to what it become right now. And the goal is to bring machine learning community together and unite around the idea of knowledge sharing and experience. So the center of AI conversations is our community and our speakers. So we meet once a month, and one of our community speakers present a topic that is centered around data science and machine learning. And so far it's been like a year, and it's been great. So we encourage everyone who is either work in the field or study or does business and want to share something about data science, ML, or AI. We have a form that you can, it's a Google form, please fill it up and reach out to us. We'll give you more information about how to become a speaker, and we'll help you if you don't have experience or so that's very encouraging. Few notes about the code of conduct. We try to be informal but yet professional community, so please respect each other, and if you see some appropriate behavior, please make sure to reach out to me and our group to report, and we'll make sure that it will get it. Capital One is our main sponsor, and this event would not be possible without Capital One. So with that, I'll pass the mic to my co-host, Ian.
All right. Hello and welcome. I love this turnout tonight. So just a couple things. Capital One is sponsoring this event, providing both like the space that we have here and also the pizza for tonight. Yeah, we love pizza. Let's go. I would say, just as a heads up logistics-wise, Capital One is providing the pizza, but the snacks and the drinks in the fridge are meant to be like for associates only. I would recommend trying to avoid those. However, we all need to drink something. So there's cups in the back over there, and then feel free to drink from the tap. And then we also have like water machines over on this side over here. Otherwise, if you're looking for bathrooms, the men's is just behind this wall over here. And then if you're looking for the women's, it would be down past this door, down the hallway, and you turn left at the big red stairs. If you have any questions about the space or about Capital One, let me know. And if you're looking to work for Capital One, because you showed up at this meetup, then that gives you some exclusive access. So I've got these QR codes that are along these walls and also some various tables here. And that gives you information to figure out how to contact me to get a referral to work at Capital One. We are referring for managers, software developers, product people, AI people. If you've got a job, I'm sure we're probably hiring for it. And if you have any other questions related to that, let me know. Yeah, I'll hand it back over to Vlad to introduce next steps.
Thanks, Ian. We have a few more QR codes to show for folks who joined from Supermomas. This is a QR code that you can scan to get some coins. There is also like a QR code printed out around the room, so that's not the only chance for you to scan this code. Few more announcements. Next week we're gonna have like online workshop. It'll be run by Shafiq. our X speaker, and we're gonna build a multimodal AI based on the open source model. That's super excited, and it's much more easier to attend. We'll have 4 p.m. January 23rd. The event will be on our Discord, so make sure to sign up or like reach out to us. We'll give you more details. Minor announcement for those of you who happen to speak Russian. There is going to be a Russian speaking hackathon. We're going to run it online, but soon after that, we'll run an offline hackathon here on this venue. So stay tuned for announcement. Yeah, this is just, it's going to be on Russian. So, with that said, I'm gonna pass the mic to Seva Oparin, the independent researcher who's gonna talk about NeRF. Thank you.
Hello, my name is Seva Oparin. Thank you, Vlad, and organizers of this event to give me the opportunity to give a talk. Yeah, as words else here, I'm an independent researcher. I have an opportunity to dive into various topics, and today I want to talk about NeRF. I know there's a lot of active development happens right now around LLMs, various generation of 2D images, and so on. And there is some sideshow on the 3D world, basically how we can bring real objects into 3D or maybe generate new 3D out of text. And I want just to talk about one of the ways to do it. But first of all, why it's generally interesting topic? Basically, it's quite a big market. Right now, we have a market of 3D entertainment, game developers, video effects. Also, we have architecture. This is the classic part. And also, it might be very interesting for us to bring 3D objects because there is an active development of robotic foundational models. I think it's that we industry right now sleeps and dream about how to make foundational models for robots. We need a lot of data, but this will be spatial aware. And it's quite important for us to bring the models that will help us to bring more data quality. So how can we do it? First, there is a simple option. We can hire 3D artists because this is high quality. It can draw us arbitrary object. But the problem is it takes some time. And also, it doesn't scale really well. Another option, we can run a 3D scan. Usually it requires us some special equipment. It might be expensive, but still we may have a high quality product. The only important thing that we must have object present. Because if there is no object present, we cannot 3D scan. This is generalization of this way, that is called photogrammetry. We will focus on this part today. What happens in photogrammetry? We have an object, and we have arbitrary pictures of this object. It can be done just the usual iPhone, for example. Based on this object, we run a fancy algorithm that brings together all the images and helps us to make some 3D representation of this object. The quality of this object might be not so high as in previous options, but with any improvement of an algorithm that helps us to make a 3D representation, we simultaneously improve the quality of all the objects that we can have via these images. So you might ask, Seva, you promised us to talk about NeRF. Where is NeRF? NeRF is here. It's on the diagram on the right. Here's the outline of what I'm going to talk today. We want to go through the path. First, we have just lots of images, and most likely we don't have any information out of these images. We need to process these images that will give us some representation of the object that will be digestible by the framework to generate 3D representation, with a full structure from motion. Once we get out of the structure from motion 3D structure, we can use it to run various algorithms. Particularly, we will talk about how to run algorithms. And once we get the NeRF, we can basically use it, for example, to render new view based on different camera position. So this is our general plan. Let's talk about structure from motion. Structure from motion is a pipeline. The idea is the following. We solved the following problem. We got the set of images. Most likely, that's all the information we have. Sometimes in metadata, in the images, we may have additional parameters, say focal length of a camera or something else. And we want to have to build a special thing called sparsity structure. The idea is the following. We want for each image to find the camera position and camera intrinsic parameters that I use to take this image. So we interested just to make the position, angle, intrinsics, and also as a byproduct of structure from motion, we'll obtain point cloud that will help us to identify general structure of object. Here's a video that represents such a structure, a sparse 3D structure. In the middle, you see the point cloud, and around you see recovered camera views. But apex is the camera position, and the red base here is a projection plane where it's like the object is projected to. There are various ways to solve this problem, but most likely if you try to run any package from like NeRF, from Gaussian's plugin, you'll bump such a tool called FallMap. Initially, this tool was developed before developing NeRF Gaussian's plugin. The idea was that, okay, we have a tourist attraction, and lots of tourists made a lot of pictures of the same attraction. We want to recover 3D structure of this attraction based on these various pictures. I think it's not official decoding of abbreviation, but most likely it's called collaborative mechanism transform. As you may see here, the performance is quite complicated. It's modularized, so each block can be exchanged for another one. But I will focus on the main part, how FallMap works. It's not crucial to make a NeRF to understand it, but it's important just to demystify it and to understand how FallMap works. So, what are the key steps in the FallMap? Again, I repeat, we have a set of images. We want to recover camera positions and camera parameters. We want to based on images, recover camera positions, camera angles, and intrinsic camera parameters, like the focal length, for example. Generally, FallMap works in the following steps. We grab an image, a single image, and we want to find the reference points, some kind of interesting points that would be easy to find on any image. For each point, we build a descriptor. Descriptor is a special thing that describes the interesting points in such a way that if you would rotate it with the camera, maybe in some axis that looks into the point and maybe just make some wiggling, resize the image, it still stays the same. Once we build the descriptors for each point, we can run matching. That is essentially, okay, we see two images here, and we see, okay, there's a lot of points that have the same descriptor. So we can run the matching algorithm that will help us to identify, okay, probably these two images look at the same face of the object. Once we got the images that look at the same object, we can run triangulation algorithm that will help us to recover 3D coordinates of the interesting points that will become point cloud in the end, and also camera parameters. Does that sound clear? Maybe any questions? Maybe fast, yeah.
Would this work so this would all work for the same image taken at the same time, right? Because if it was taken at a different time, suppose you want to create a data set of the same object. If it was taken at a different time, it might be at a different length, or it might be like a bit more closer to the object. Because in this case, like if the two images are too different in size, would the call map still be able to map them together?
It should, yeah.
So it's scale invariant?
Just to explain what happens here. Later on, I'll explain more details how call map works. But generally, you have several problems here. Yes. First one, you may have different kind of cameras. Yes. For example, we have focal length 22 millimeters and 70 millimeters. Yes. So the object will look a bit different. So based on these descriptors, we'll make in such a way descriptors that will be obvious to. It still be possible to match descriptors with different size of the images, including some rotation, maybe some different positions of the camera. It's kind of conditional. It's not like we can grab arbitrary two images and look at the object and we'll get a match. But if, for example, you see this kind of two images that make kind of huge overlapping of the same side of the object, it will help. Separate two problems I see here that you may take a picture in different conditions. Like you may have different lightings, you may have different exposition, different, you may have also some noisy objects. For example, here at the bottom of the building, you see some people. People tend to move, unfortunately. And we will make such a descriptor and such a matched algorithm that will help us to overcome such problems. It's not guaranteed, just in case, but we'll try to deal with this. The question is, what is descriptor? Yes.
How do you define it? Like manually, and there's an algorithm.
Yeah, there is not an algorithm, but algorithms, various types.
Could you repeat the question?
The question is the following: how do we define the descriptors? I'll talk about descriptors later. Just here, just I'll outline. But generally, there's a more classical algorithm to make a descriptor based on some kind of kernel trick and gradient trick, and there's some learnable way. So we can apply again special model that will make kind of feature mapping from each interesting point, some feature vector, and we can compare feature vectors so to see if the point looks like the same.
Is it defined like just one image or all the images of the same object?
Descriptors are defined per point. So we have an image. In each image, we have multiple interesting points. For each interesting point, we define a descriptor.
So it's like it's done independently for again.
Say it again?
It's done independently for every image.
Yes, it's defined independently. Actually, I'll talk about descriptors, so I'll probably answer most of the questions.
Do you know the distance, like from the camera to the points you're marking?
To what?
Do you know the distance from the camera to the points that you're marking?
No, you do not.
No?
You'll try to figure it out. Sometimes you'll maybe lucky, but you have focal. You might be lucky to have a focal length in EXIF. It might be helpful, but you don't know the distance. You try to triangulate. Let's talk about feature extraction. How to find an interesting point and build the descriptor. So here, just a general description how it works. First, we localize interesting points, find the coordinates on the image. The idea is very simple. We can run very classical algorithm. It's like convolution on the 2D image. And this convolution may help us to find edges on the image. It's very helpful because it shows us what kind of, we can ignore all the flat part. For example, image in the middle is obtained just making blurring image twice in different space and find the difference. Very simple. Second, we run a coordinate detection on the edge. The reason why we run coordinate detection because just being on the edge doesn't be very, I would say, specific. Coordinate detection is also some kind of convolution trick. We just run convolution on the 2D images. We get some numbers, we make some subtraction multiplication, nothing very fancy. And based on conditions, we find where we have kind of corner of the edges. It's called Harris corner detection. You can find it on the internet. It's quite simple. Okay, we localized interesting point. Now it's a good question how we run the descriptor. Okay, let's consider the image. The image, I have to refer again to repeat what I was. We want to make this descriptor with this independent rotation, small wiggling of the camera, some resizing, and also it would be nice to have it independent of light. What we can do? Let's consider the image and think of this as a landscape. So we think that we have a 3D landscape, yes? We have x, y as a coordinate of a point, and if we convert the image to a grayscale, we consider the color of a pixel as a height. Yes? So it's kind of this landscape. And we find the gradients. So first problem we can solve is how to avoid problem rotation along the axis. Basically what we do, we find gradients in the vicinity of an interesting point and make a voting mechanism what's the majority of the gradients look into. And then we just rotate the image so the majority will point upwards. In this way, we can avoid some kind of problem of rotation of the camera. Also, we built just make a rectangular square patch around interesting point and just make kind of sub-patches and find the gradient directions and build a histogram based on these gradient directions. What approach? First, if you look at the gradients, the color of the image doesn't matter. It helps us with because some different lightings we can be oblivious to this. Second, assuming that we have about the same size, just the change in width of the camera doesn't change much of this histogram, so will be the same. And another problem that we may have different sizes of the image, yes, of the same point. So we just make a pyramid of the image, like we make an image with smaller image, with smaller and so on, and build a descriptor around each point for each size of the image. And so we can find comparison based on different resizing. And so we can become oblivious to the size, kind of focal length of the size of the image. This is kind of general description. You can find more detailed tutorial about how to build descriptors. But important thing you can see that it's not some very special magic here. We can make quite oblivious descriptor to different changes of the camera positions, lightings, and so on. Also, there is some research around this topic. We make a PhD around this topic, make some special models, extract some features around this interesting point to make it even more precise. You have more questions about descriptors? Okay, I hope I answered. Okay, we do descriptor.
My question is about the gradient here. I don't know too much about cameras. So when we say gradient direction, I thought you meant color change. For example, lighter going darker, darker going lighter. But you also mentioned color doesn't matter here. What does gradient mean?
Look at the direction of a gradient. Probably this answer why color change. I think the question is why bigger difference of color doesn't make effects, yes? Kind of amplitudes of color.
Yes. So my question is, I thought when you use these directions, I was following. I figured that's some sort of color change. For example, castle to the sky, it's darker going lighter. And when you rotate them, I kind of got lost there into one singular direction. So I wasn't sure what you meant when you say color doesn't change. I'm just curious, like when we say gradient direction, do we mean color change or direction of color change?
Okay, probably I can answer this question with detailed description. First, again, we computed the gradients, and essentially what we do, we normalize all the gradients. So all the gradients has a length 1. Here, for example, on the bottom left diagram, what we do, we build a histogram with a step of 10 degrees. Yes? So we have 36 directions, we build a histogram, and we have a kind of bulletin mechanism that says us where we have most of the gradient directions. The length of a gradient doesn't matter. The important thing only is the direction. Why we don't have kind of flat histogram here? Because we choose this interesting point in such a way that they are corners. So they will definitely have some strict direction.
Thank you very much. I think I follow you. Trying to find the general direction relative to maybe the lightest spot or the darkest spot.
Yeah.
Thank you very much.
I just wanted to add what a gradient, the gradient is like the three-dimensional, multi-dimensional version of a tangential line. Yeah.
These gradients computed on like grayscale images, right? Or are they first converted to grayscale for SIFT, or is it done on RGB?
I assume it's a grayscale, but I will double check.
I think it's
the question.
The question is if the gradients are computed on a grayscale or on RGB. I would assume it will be computed on a grayscale,
Yeah.
but I'm not 100% sure. So probably it can be computed different channel settings. Yeah, we're going to make sizable function. Okay, we build these descriptors. We can now compare points from a different view, can understand if they are the same. And then what we want to do, we want to make a matching. Matching mechanism doesn't require us that all the points that we see will be matched, but we just want kind of robust matching that most of the points will be similar. Whereas usually there's some kind of threshold where, okay, if we have enough of points that are matching, then good to go, and we can say, okay, this image just seems to look at the same side of the object. Once we get it, we can solve triangulation problem. What we have in triangulation problem? For each interesting point that are matched, we know the 2D coordinates of this point on a 2D image, basically on our pictures, two pictures, yes? What we do not know, the 3D coordinates of this point in a 3D space, and also we do not know camera parameters. Depending on camera parameters and these coordinates, we can build a system of equations, maybe linear, maybe not linear, depending on the camera model, and solve it. In an ideal world, of course, we may find just exact solution, but in our world, we may have some mistakes. So usually it is used robust solution. Robust solution means that we try to find such a solution with camera parameters, 3D coordinates, that will satisfy most of our equations, our data points here. And basically, we get 3D coordinates. We just repeat this process, or we add in additional pictures. Additional pictures we translate, we try to fix the camera position, we may tweak a bit the image position, coordinates to a point file, but in the end, we obtain this picture based on our multiple images. There are some takeaway lessons from here. If you plan to make your own custom dataset for NeRF, for Gaussian spot, whatever, if you want to put it in the column, first, you want to have lots of informative images. What does it mean, informative images? It means that it has a rich texture. If you look at the ceiling, completely white, some kind of noisy, it won't be helpful. If you look at some kind of projector here that has a lot of corners, a lot of edges, it will be helpful for us. Second, again, just looking at the algorithm, you can understand that it's good to have non-blurry images. It can be very clear images without additional noise, and it will be very helpful to build descriptors. Also, out of the matching, you can see that it's good to have a good overlap. So if you have pictures of images from this side and from this side, and there is no overlap, then it will be really hard to find the matching. So you want to make a good coverage around the image with multiple pictures, maybe video, that would have overlap, it helps us to make a matching, and helps us to build a nice sparse 3D structure. And yeah, these interesting points. These interesting points that we extracted with the 3D coordinates would become a point cloud. For NeRF, it's not very helpful, but if you're going to study Gaussian splitting, it will be very helpful to understand how they come from, where they come from. Yep.
So I have a question. You mentioned about that. You mentioned about the needs like informative like images like so as we take that much of images like is it possible that we use a video and take it by frame and make it also invisible?
There's pros and cons. Yes, it's first of all, of course, it's possible to use a video, but you have to make a video in such a way that will obtain lots of precise frames. So if you take a video, usually if you just make a stop and it replace, you see like it's blurred images in the middle.
Okay, so that brings me up the interest, which is what should the compression be and what's the FPS of the video that is ideal?
In terms of FPS and compression, I won't answer you. Just assume that you want to have clear images with no blur, no noise. I mean, not no noise, but as less blur as possible, as less noise as possible. And you just need to have a good overlap.
Get it. So it'll still be images to be ideal. Make it.
Yeah.
Get it. Thank you.
The result that you showed, that 3D result, how do you know that it's good or bad? Like, how do you measure that?
One of the good measurements is at least how many images you got matched, first of all. Because if you have 1,000 images, but all the 3D sparse structures that you managed to obtain, say 10 images and 20 images, it might be not so good. You can have a visual inspection of this. Also, inside the pipeline, there is such thing like geometry verification. But based on much tries to understand, does it make sense or not? Some button adjustment. But basically, for you as an end user, it's visual inspection of what you see. After the talk, I can show you how the lab looks like on the laptop, if you're interested. But basically, yes, this one and how many images you get matched. And also, I might probably give you some metrics.
Can you scan?
Hmm?
Can you scan like instead of taking like a photograph?
Yeah, the problem with scanning that you have to have special environments. Of course, it's good when you can link an Apple in a studio. You have a nice lighting. You have cameras, not only cameras, but laser beams, and you can read all this information. But sometimes you cannot bring Coach into a studio. Maybe it's be more pricey to bring Coach.
So you can do it.
You can do it, yeah. Of course, it's one of option. But in our problem, the option must exist. It's also quite
I was thinking that versus like printing, 3D printing.
Yeah, but 3D printing is outside. Here's like the input.
Yeah, I know. I was just thinking that's from the scanning properties.
Yeah.
That you can scan.
And this is the options.
So what's the minimum amount of images you can use to do this?
It depends on the object and how complicated it is. My experience with, for I took a picture, for example, pyramid in Mexico. I need about 270 images. It recovers kind of modest quality. But the more images, the more overlap you have. It may be sometimes not so important to have lots of images, like a good coverage. If you have 1,000 images from one side, but not from all other sides, then you won't have a good quality. This probably is more important thing.
Can you do partial scanning? So if you have a lot of images from one side, you can just scan one side, create a partial.
Yeah, for sure. Again, after After the talk, I can show you some demos. Unfortunately, it's not on this laptop, but if somebody is interested, I can show you.
How long does it take? 200 images.
Oh, it depends on CPU. It takes about hours. If you manage to use GPU, usually about maybe 2-3 minutes. It's important to invest into compiling whole map of GPU. Okay, next step. I talked a lot about whole map. Now you can forget about whole map. Only thing you have to remember that initially we have a set of images, but now together with images we have full camera parameters like this: position, angle, focal length, maybe some additional information. And we can approach making learnable 3D like solving a certain problem that's called local view synthesis. The idea is therefore, we don't focus how exactly we represent the 3D object. We only reason why we want 3D object to make arbitrary camera position, so we would be able to render new view with this object. So we can state this is a problem. We were given sparse structure, we're given camera parameters, where this angle, focal length, and we are asked to render new image. So the idea of generally learnable 3D structure based on images learn the structure, and based on learned structure, we reproduce new renders. This is kind of general framework. What happens inside, be it NeRF, be it classic mesh, be it Gauss plugin, doesn't matter. We're just solving this problem. As I promised, I approach the NeRF. What is the NeRF? The idea of a NeRF is to represent the 3D object as a kind of field that emits light. So we can imagine that you have a 3D space, and in the 3D space you have multiple particles. Each particle emits the light of a certain color and have certain opacity. Opacity means how lighted the light will go through this particle. And we want to model this field that radiates the light using neural network. So this is the neural radiance field. More formally, we build a function. Aside of coordinates, we also want to assume what the angle at the object. Why is it important? Because we may have some metallic objects. So we have a reflection of the light, and then which will the object may matter. So we have a function that takes as an input the coordinates of this particle, the angle at which we look at this particle, and the function produces color of this particle and also the opacity of this particle. As drawn in here. So let's put some questions to understand how NeRF works. We have 3 questions. First, we build such a fancy model, how we render a novel view. Second, once we learn how to render a novel view, how we train our model. And third, maybe we have some special nuances about input and architecture. We will talk in the third part. Let's talk about rendering. Rendering in NeRF works similar to maybe ray tracing, maybe ray margin output. We have a camera, yes, and we have an image plane. What do we do? Through each pixel of the image plane from camera, we launch a ray. And the ray penetrates the cloud that emits the light. We simulate the following physical process. We met first particle that has non-zero opacity. We said, okay, with probability of this sigma, with probability of this opacity, we stay here, we obtain the power C of this particle. If not, with probability 1 minus sigma, we are going to the next non-zero opacity particle. Yes? We come to the next particle and repeat the process. So for the kth particle, just product 1 minus sigma for all previous particles times the probability stays here and times the power we get. and we just sum it all together. So it's kind of expected color based on how lightly we stop the particular particle. Here at the bottom, there's a formula in integral way. Basically, we start from the beginning of the line. Exponential here with the integral means we just make a product. We can find the probability that we pass through all the particles before. And here we determine the second integral here that okay, we pass all the particle before, we stand in this particle and all the color of this particle. We can put such integral that the expected value of a color, and we obtain the color for particle on single pixel. If we launch this ray through each pixel in the image, we'll obtain the whole picture. That's sound clear now?
I don't understand the connection between the wavelength on the size of the nanometer wavelength of light of the different colors, and how your I don't know, it's the probability density. What's the connection? How do you find the color based on the probability?
Color is an expected value of the colors represents a particle particle.
Thank you. Thank you.
Okay, probably somebody should ask how expensive it is, because we have a high resolution image. With a high resolution image, we have one integral, second integral. How are we going to compute it?
How much compute do you use?
Let's just optimize and then ask the question.
The first thumbnail video on YouTube said that now you can do ray tracing in seconds.
Okay. The answer is the following. We'll execute sampling. Basically, we have a frustum, yes, of a camera that is, the camera doesn't render the whole 3D space, but you have two limitation planes. That's kind of near plane and first plane, and we want to render what is in between. That's shown here. For this frustum, for each ray, we separate, basically we obtain the segment, and we split the segment into n smaller segments. And for each smaller segment, we sample randomly a point on this segment. And for this point, we compute the color and we compute the opacity. And we assume that the opacity and the color extends the whole segment here. And based on this, we again repeat the process, but now with summation, this process can be done in one linear pass.
Monte Carlo sampling? Monte Carlo?
Yeah, can be called Monte Carlo. If you want random, it's called Monte Carlo. The only thing here we have in the original paper we use hierarchical sampling. It means that there is two nerves. One is first nerves that use this sampling, and second nerve is modified that makes the weight of the sampling based on how much density we have. So if, for example, here we have points out of our color, it's kind of non-informative. We have very few samples. If we have a big density, then we have more samples here, so we achieve band-rendered quality. Okay, we learned how to render. Now we see part how we train. Training is quite simple. Actually, we just run, we take an image from the train set. We know the camera position of this image. We ask our model to render the same image, and we just find minimal square error. As you can see from the rendering, it's very important here. Rendering differentiable. So all the computations here is kind of keeping ground.
Regression. The camera position is known from the sparse reconstruction.
Yeah. So we can render the image because the rendering process is differentiable and what function is differentiable. We can use the simple Gaussian descent and obtain the weights that fits us the most. Also, we can save a bit of time computing. We may avoid rendering the whole image. You can just say, okay, we want this and this and this pixel, simply randomly sample and render only particular pixels and compare them. It just helps us make a more smooth learning. And this is model training. Okay. The authors of the paper run all this model and notice that after the training, they get the image something like on the left. There's a problem here. We use MLP. On the MLP, we provide an input like X, Y, Z coordinates. And if we make a small shift in the coordinates, it's hard for the model to make abrupt change in the output. So the solution is quite simple. We can make a positional encoding. Basically, we make kind of Fourier transformation. I forgot to mention, we input to the model, we usually assume that it's normalized. So basically, coordinates from -1 to 1. It's good for models to have a small coordinates normalized around -1 to 1. We make a Fourier transformation. We still preserve spatial information, but also even small change, small shift in the pixel can be detected by the model and used to render new kind of render better change in, for example, orders on the image here. There's a hyperparameter N here. A latest study in the paper shows that it's better to have a larger N than a smaller N, but basically it is until we have 2 to N is around resolution. So after we obtain 2 to N, a bigger than resolution of our picture, basically it's starting to become informative and the quality systems grow. Also, yeah, I put in here, I think Vlad will publish this presentation on the website. There's an additional paper, separate paper, that make a whole new research about how better to use positional coding. Positional coding here is not the best, there's better positional coding. If you want to see details in here, you'll don't know.
Yeah, just want to say that we'll publish materials in our Discord Discord server in event materials channel. So if you have not yet joined the Discord, reach out to us and we'll show you the link.
Thank you. Okay, and the last problem.
So just a follow-up on the Fourier transform. I don't know if this is a silly question, but do you ever encounter Gibbs phenomenon? And what does Gibbs phenomenon look like when you have many sinusoids added?
Can you make more clarified?
So when we add many sinusoids together, like around.
That's okay.
Sorry. Around the end of the wavelength of these sinusoids, they tend to add up, right? When we try to model for sharp functions. So I'm curious if you encounter that kind of issue. Is that not a
I'm not sure I'll be able to answer this question, but again, there is a separate big research about how to better adjust Fourier transformation. It's kind of how much information we can pass through these components. I think you better look at the show this.
The function is differentiable, it's continuous.
It is, yeah. Okay. It was, but probably you want to check out this paper. Because it's not very fast.
Yeah. Try to help you.
Yeah, I recommend to check out this paper. Probably it's better to look at this.
So this is to put like the pixel values into like a higher dimensional all.
Pixel values or big pixel
Yeah,
coordinates.
it's a problem because we're trying to make the differences bigger, right? You know.
The problem is the following. Yes, you.
Could you repeat the question?
Yeah, probably.
Maybe I'm not following at all. like if you P's for like the value of the pixel, like the intensity, I guess, whatever. Or am I wrong? Am I totally misunderstanding?
The problem is the following. You have x, y, z coordinates. If you pass the x, y, z coordinates, basically the smaller we change the coordinates, the more likely you see the architecture here is a value of MLB, yes? Not very perceptron, it's not very complicated. We may assume that it will be sensible to the special coordinates, but generally the small change of coordinates doesn't guarantee us that we will have a big abrupt change in the outcome, in the output of the model. You can even see here basically what happens that the model segments the image into multiple like triangle, maybe polygons, and just define the more or less the same color. It's not able to reproduce precise image. It's also kind of over smooth it. And what we want to achieve here, the following: we want to have two conditions. First, we want to still preserve spatial information. Like if you have two pixels next to each other, their representation should be the same. But at the same time, we should help the model to understand that they are different pixels. Don't think they are completely the same. It's like feature engineering here, but solves these two a bit contradicting problems.
I think the last word you said. I heard most the very last one.
Contradicting conditions.
Okay. Yeah. Thank you.
Talking about architecture. Architecture is quite simple in NeRF. Generally, we want first, we have a condition that it should be small because rendering takes time. Architecture itself is a modular perceptron with real layers. Golden trick here is good to look at that we have a backbone, and then on the backbone we produce opacity of a particle plus feature vector. And only after that we have additional layer, and then we can do the color. This is kind of regularization to motivate the network to first learn the structure of the 3D image, and only after that to make the color on top of this. There is quite an easy trick here because you see this image. Technically, the model can be cheated. Instead of rendering 3D in the middle, it can take planes for each camera and just render separate planes for each camera position. So instead of the object in the middle, we will see just multiple planes here. So this trick hopefully, not hopefully, but helps us to avoid such a problem. And basically the solve for NeRF itself is kind of vanilla version of NeRF. Of course, it's not the end of the whole NeRF direction because we have lots of problems. The first problem is anti-aliasing. If we look at kind of specific distance to NeRF, it looks good. If we start to go closer, it's either become blurry or some kind of, like resolution of nearest pixel. We have aliasing. There's a tricks to make anti-aliasing. We may have a problem with kind of people. It can look as SF, unfortunately. If we can add special additional value how much we pass certain region, there's a problem with kind of, we assume that the scene is bounded of the 3D object. But we can make it kind of unbounded. Some special techniques to improve quality, also special techniques to make it more flexible in terms of saving information not with a single element, but some kind of feature voxels. And also I recommend an event, if you do this thing, you get a YouTube video from the authors of the NeRF. Definitely worth to watch this in more details. Overall, NeRF is about NeRF itself, probably with all Fourier transformation, and also how to bounce moving objects. And the last two examples that I made in separate slides that I find really interesting. Recently, there's published results called link validation method. It was quite fancy. it says that we in before learn only RGB colors, yes, and opacity. But on top of this, we can learn also language embedding. So for each particle, we see what object this particle belongs to, and using classical clip model from the image, we get language embedding from this particle. When we can type embedding, for example, where is Alpha, and it says, okay, this embedding looks similar, so it highlights where is Alpha. I think it's quite fancy. In practice, it doesn't work really well. This with proof of concept really fancy. And the second application,
Yeah, and this one, are you saying that? Could you repeat exactly what's happening? Because I understand that they're passing the XYZ and the basically the viewing angle to the number as well as the scale. Are you saying like NeRF, which gets out the RGB values, they're also getting out dynamo features and clip features?
Just again, to repeat that. The input always the same. The input is the coordinates of the particle and the angle of view. That's all. No less, no colors. The output can be more rich than just the color and the density. For example, we can look at the image, the particular site, we can try to repeat for particular patches and start to make for each particle in this field of view language embedding. So we can change your learn language embedding actually inner features, just separate features, just has the quality. But important here that we can learn features out of this.
Got it. So because that diagram is a bit misleading then. So basically the NeRF puts the RGB and then the dynamo features and the clip features are the separate models and they're all being used for the final language loss that's used in training.
Yeah, I'm not presenting this paper, this is a general generalization, not precise. But I just think that there is such an idea that we can render in addition language embedded vectors, and it can be very helpful. And second is also released from Microsoft, Paris. There is a quite active field of development about how we can generate 3D based either on a single image or on a text even. They just grab big data set of 3D objects, make kind of a model that can help us to build 3D latent representation of the object in a 3D space, like the 3D blocks with features. And then these 3D features can be converted in the form that is most convenient for us. Can be NeRF, can be mesh, can be Gaussian slide, and it can be used. What I like about this, but usually before the quality was not so great. Right now, it looks like if you have some indie game and you're not very demanding about the quality, you can just use this model out of the box. Looks to me really like ready for results. And that's all. Thank you for your attention.
We have more questions here.
Are you adding the linguistic data to the same vector that has the raster information, like for the point, for the interesting point?
I'm not sure I understand the question.
How are you connecting, like, where's the local question? Oh, okay, sorry, didn't work on that bit.
I don't work on this paper, but I just describe complex. In general, what we expect, we have a model that for each particle produce both color of density plus produce clip features. Also produce linear features that were like a visual transformer. And based on this clip, from clip we get from the values, from text we run the clip, we get again language values, and then just see the cosine distance. Is the cosine distance like close to 1, very similar?
So we're probably going to have a chance to ask several questions after the talk. And thanks so much. That was awesome talk. that being said, like, thank you so much for coming. And concludes our today's event. And we're gonna fix here for probably 20 to 30 minutes for the networking, and Seva gonna be here. He also can show some more demos on his laptop, his NeRF. So people make sure to stop by. And after that, we're gonna go for the fight at the bar. Should have our over here. So if you want to stick for a bit longer, feel free to join us and in the whole town bar. Thank you.